Hi, I'm Joel Kira from Georgia Tech, and I would like to thank the workshop organizers for inviting me to speak. And today I'm going to be talking about ingredients for open world cross-modal interaction. Anytime we talk about human-robot interaction, we can specify exactly what types of interactions we're interested in. In this case, my group is focused on perceptual learning, and so we're often interested in interactions that can promote learning. And this includes learning about new objects or categories in the world, or even learning new policies that allow us to map images or other types of raw sensory data into how a robot can potentially act. There's lots of different types of feedback that we can think about. For example, natural language instructions that a human can give, or actual demonstrations, or natural language descriptions of new types of objects or categories or environments that a robot may need to learn about. And so one example that I tend to think about is this cycle where, for example, a robot can describe what it's seeing, so mapping perceptual inputs into natural language descriptions, for example, image captioning. The human can take that kind of natural language inputs and perhaps provide feedback in order to correct the robot's knowledge. And then the robot can react to that feedback, for example, by retrieving information from the web or other types of natural language inputs, or of course, images and videos, and it can ideally continuously learn about new types of things that it did not know about before. And so we can think about what are the ingredients that are necessary to enable this type of cross-modal interaction. Now, I posit that there's a lot of different types of things that we may need, both in terms of the research itself, but also things that can catalyze the research. So I think simulation and settings and tasks is very important. And so we have a range of works in this area, including making traditional computer vision type tasks more realistic, that is robotics-like, as well as speeding up simulation, for example, through Habitat 2.0, which I'll talk a little bit about. Of course, language here is really important. That's the point of this workshop, so cross-modal interaction. And really language and grounding, that is the association between what the sensory data that the robot is obtaining is with respect to that language, is very important. And there's a lot of different aspects that language can provide, which I'll again talk about. Of course, we would like human feedback through natural language to actually provide information that the robot can use to continuously learn about new types of things. And that's by itself is not even a trivial thing. And so that's a separate set of research areas that are really important. There's a whole bunch of other areas that I posit are really important, such as semi-supervised learning and open set learning. This is because robots often get lots of unlabeled data, and really what you have is very sparse human supervision that the robot needs to learn from. And I also posit things like efficient fine-tuning is really important. For example, when we want to do onboard learning, on-the-fly learning by the robot. Really, in this talk, I'll be focusing on the first three here. And so kind of as a motivating type of task, we can think about something that probably a lot of you already know about, for example, language guided navigation. Here, a human provides natural language instructions to navigate through some environment. This can be in the real world, or often we use simulation or photorealistic environments from 3D reconstructions to allow a robot to navigate this environment without access to a priori maps or explicit knowledge of goals, for example. And so here's one example: exit the room, make a right, head straight until you reach the entrance, and to the next room and wait. And so a lot of progress has been made, a lot of it driven by things like 3D reconstructions obtained from great sensor data such as Matterport's sensors. And this gives you typically both RGB, but also depth information as well, and things like panoramas, for example. And so kind of there are several things that are involved in this, and we, in our ICRA 2021 work, have really made this task more realistic such that we can do it on real robotics platforms. So for example, we introduced continuous controls formulations for VLN. The typical original vision language navigation tasks often involve just bouncing around between different viewpoints as opposed to having continuous robotics controls, and which we felt was important, for example, in order to make the tasks more realistic and long horizon. That is, the robot will have to really navigate across much longer trajectories. And here again, just like before, you still have first-person visual observations. And there's several key things that one must implement when solving this task, including decoupling, reasoning, and imitation. You have to perform some textual reasoning, of course, because the instructions come in the form of natural language. And of course, cross-modal grounding is really important, where association between language and what the robot is saying is important in order for the robot to actually determine what to do next. And especially when we add these robotics like continuous control formulations of this task, there's a whole other set of things that are important. For example, long horizon temporal reasoning, low-level neural controllers, and so on. And what we showed in our paper is that really you can develop interesting architectures such as hierarchical cross-modal imitation, where you have a high-level policy that's outputting high-level actions, for example, left, right, forward, backwards, and these high-level actions are enacted by a low-level policy that actually turns them into low-level velocity or angular velocity commands. This is some example of, again, the continuous controls where we have long horizon trajectories rather than bouncing around from viewpoint to viewpoint. Of course, you have to avoid obstacles, you have to squeeze through doorways and so on. And so our approach was, again, this hierarchical architecture, and this really emphasizes the cross-modal nature, where we have textual reasoning, so you can have some language models, such as the traditional transformers or any large-scale language model these days, which we didn't use at the time, but of course can be used. Visual spatial reasoning in order to actually take into account the RGB and depth information. We need some sort of cross-attention or cross-modal transformers that can integrate information across text and vision. And then this can be used to determine what high-level action to perform. So there's a decoder that takes into account the cross-modal information and outputs what action to perform. And then, of course, this is translated into low-level temporal reasoning. Again, in this work, which was last year, early last year, of course, used LSTMs, but these days you can put in your favorite transformer pretty much all over the place, including in the visual encoding part as well. And then you finally have a neural controller that enacts things. And of course, this architecture it enables much better success using this hierarchical bias in the architecture design, and we get much better performance across a range of past state-of-the-art at the time. Here are some examples showing failure modes. For example, in the flat architecture that did not have this hierarchical agent, it tends to bump into obstacles and things like that, which are much more problematic, obviously, when enacting a continuous control formulation, whereas the hierarchical method is able to really avoid these obstacles, squeeze through doorways, and so on. Of course, it's not perfect still. It still has failure cases, but it does much better than a flat policy. And so we do have some other work that I won't talk about too much, but quickly mention that we have some recent work where we also showed that self-supervised learning can significantly aid vision language navigation. So here are the opportunities that robots can gather essentially free unlabeled data by just wandering around environments. And so we can leverage this through some self-supervised tasks that we designed. So we both took existing self-supervised methods such as MoCo V2, but also designed some interesting embodied self-supervised learning methods. So please do check out the paper, and this led to significant performance gains when added to all sorts of different architectures. So the self-supervised pre-training is actually orthogonal to what you actually use to navigate. One interesting idea that you can potentially think about, and we haven't really done yet, but you can try to not just use the current masked autoencoders or all sorts of different transformer-based self-supervised learning, but really use that kind of notion to predict everything from everything else. So I think this has been laid out in the past as well, but I think there's a lot of opportunity when you are working in a embodied task in order to predict, for example, actions, futures, temporal futures, spatial and geometric reasoning, and all sorts of consistency losses that you can use across these to really improve your feature representation, which will ultimately improve your reinforcement learning policy. Okay, so that's kind of some work that we've done. Some recent work that we have done in simulation to really push the boundaries of this to add things like physics, which vision language navigation does not have, is this our Habitat 2.0 work. This is with a co-advised student, Andrew Sazat, with Dhruv Batra and lots of Meta folks as well. And the key here is to have very, again, long horizon robotics tasks, but also include things like physics and manipulation. I think especially once we move to things like cross-modal or language, I think a lot of these physics aspects and common sense reasoning becomes really important only when you are able to manipulate the environment rather than just perform navigation. And so the idea is this simulator both includes physics, but also has very fast physics that can scale to tens of thousands of hertz across a cluster. And so, for example, what we were able to do is train policies for various subtasks of complicated rearrangement tasks where you try to rearrange a set of objects from one place to another. And we were able to, for example, learn the pick task, just picking up objects, navigation, placing things down, and so on. And what's cool is we compared reinforcement learning to traditional sense plan act methods. And here, these are much more traditional methods that essentially, observe the environment, plan out all sorts of the possible trajectories through motion planning, such as RTs, and then execute those through low-level controllers. Interestingly, what we showed is that reinforcement learning does really well in the scene environments, that is, under the conditions where it was trained. However, once you have new types of objects, new types of receptacles to put those objects in, the success rate actually went down much more significantly than things like the traditional planners, planning-based approaches. So here, reinforcement learning does a lot better in scene environments because we are doing very large scale training. But as new things come into environments, we really lose this generalization. And so really perceptual generalization is still a bottleneck. Of course, there's a generalization to the actual objects with respect to the manipulation, but in this case, manipulation was sort of simplified. So it really, a lot of this comes from poor generalization in terms of the perceptual feature space. And so I'm going to talk about some recent work that we've done to combine language and vision and do really cross-modal language and grounding, as well as continual learning and eventually category discovery. And a lot of this is kind of recent work or ongoing work that we haven't published yet, but we hope to continue to push in the next year or so. And so again, I'd like to think about this loop where a robot can describe what it's seeing, that is its interpretation of the scene, and this can be through methods such as image captioning. The human can react to that, and then the robot can retrieve information and react to the feedback to learn about new things. And so you can think again about how to leverage cross-modal models. This can include just language-only models, large language models such as GPT, cross-modal models such as CLIP, which align language and visual embeddings, as well as interesting new text-to-image models such as Stability AI and DALL-E. By the way, the image shown in this figure was actually generated by DALL-E. So it's kind of cool that we can also use them to do presentations as well. And so we can think about how such models can be used. For example, again, image captioning, retrieval of contextual information. So for example, we have the World Wide Web or other textual sources. Can we actually retrieve information from them to improve our knowledge? And then zero-shot or open world learning, which again is a key limitation of vision-only models, that is generalizing to the open world, learning about new categories, continuously updating our representations is still a very difficult challenge. And so I'm going to talk about several works that we've done in these areas. The first one that I'll talk about is cross-modal contextual, textual and visual context for image captioning. And here the key idea is how can we actually provide or improve context information from large-scale multimodal models. For example, in image captioning, some of the typical models essentially do object detection, typically via a frozen model, and then use that frozen pre-trained model as conditioning or inputs to transformers such as, decoders to generate the image captions. And so there's a lot of reasons why this, again, does not provide sufficient information. For example, it doesn't provide a lot of information about relationships between objects, scene level information, and so on. And so our idea is actually to use cross-modal models such as CLIP to retrieve contextual knowledge. That is, we're going to take the image, we're going to retrieve textual information that may exist in various textual databases, and we're going to use that as context. So now we have new text information. You can view this as additional views or augmentations of the image data, and this can be used to improve our feature processing such that we can then perform better captioning. So here is kind of an overview of how we do this. So the first question is, how do we get beyond just pre-trained object detectors? And again, what we're going to do is use CLIP to retrieve a set of textual data. So this is what it looks like. We have cross-modal retrieval. I'll show the architecture for this, but essentially because CLIP has aligned text and vision encoders, we can just encode various crops or pieces of the image via the CLIP image encoder, and then do a nearest neighbor search over some textual database where we find the closest match with respect to the textual embedding of CLIP, which again is aligned with the visual embedding. And then we're going to do several things. We're going to, again, use CLIP to get the image encoder. So now we're getting image level information. We're going to condition or combine the object detection outputs with this image encoding. We're also going to condition the text encodings of our retrieved tops k nearest neighbor of text that describes what's in the image. And then we're going to feed both of these sources of information, both the text and the object detections, into a transformer decoder that generates the captions. We do this via several contextual cues or crops of the image. So we don't just do the entire image, we do several different crops of the image in order to really retrieve text of various kinds. Some can be image level information, some can be object level or even relationships between objects and so on. For example, here you see toaster oven sitting on the counter. And again, this is what really gives us additional information beyond just the object detector. And so if we actually use this architecture, we can combine it with any state-of-the-art captioning model, such as M squared, which was state-of-the-art at the time, and we can improve significantly. For example, here we have over 4+ CIDR improvement, which is quite significant. We can combine it with other pre-trained models, such as Oscar, if you're familiar with it, but it performs additional pre-training, which is always harder to improve upon, but we still get significant performance boosts. So even when you consider larger models that are pre-trained, as well as VinVL, which uses I think 5+ object detection data sets to pre-train a better object detector, we still get significant improvements here. What's interesting is we can also show that if we do the low labeled setting, and even we can do semi-supervised, which I'll show later, where we have essentially a smaller amount of data, we get much more significant improvements. One thing that we'll note, and you can find in our CVPR 22 paper, is that actually we show that quantitatively we also improve grounding. So providing this textual context actually provides improved grounding, that is the association between the text and the images, which is again very important when you're doing this cross-modal interaction and retrieval of information. We have some additional improvements upon our CVPR works. For example, we can now view the textual information as really data augmentations or additional views of our image. And so there's kind of a fusion question here. How do we combine different sources of information, that is textual information that we retrieve from the image information itself, image grid features, detected objects, and so on. And so what we want to do is do this effectively, but also efficiently. That is, we don't want to just concatenate all these pieces of information and feed them to a large transformer, because as we know, transformers don't scale well as we increase the number of tokens. And so what we want to do is obviate, concatenation, but we still want to do really well. And specifically, if you think about each type of information, images, image patches, objects detected, textual information, we don't really want to encode them with separate encoders, because this wastes information and doesn't allow us to combine kind of knowledge across the different views that the model may get by combining, by having a shared encoder. So again, the question is, how can we do this effectively and efficiently using a better architecture? And so we have several kind of novel or interesting additions here to the architecture. In terms of efficiency, we treat heterogeneous views as augmentations of the input, and we encode everything with a shared encoder. And when you view kind of everything as an augmentation, you can also do something cool, which is contrastive learning. So again, there's contrastive learning across augmentations is a very well-established thing now, and so we can actually do contrastive learning between the image kind of view and the textual view that we retrieve, and get significant efficiency boosts, that is data efficiency boosts. We can also increase our effectiveness, again, using a two-tiered hierarchical architecture. First, we'll ensemble within the views, and then we'll ensemble across the views. And so we have this kind of hierarchical cross-attention. So, level 1 cross-attention and level 2 cross-attention, which again does this aggregation within the views and then across the views. And again, the key thing is that across this design, we can both get efficiency, like data efficiency and computation efficiency, but also effectiveness. That is, we're really leveraging the additional information as much as possible. So again, we get significant gains over our prior CVPR works. And even in the semi-supervised case, in this case, we can also leverage the unlabeled data. In the previous case I showed low labeled, where we didn't use the unlabeled data. Here we're actually using the unlabeled data because we're doing consistency losses, contrastive learning across the different views, which can be even in unlabeled data. We don't need labels to do contrastive learning. Okay. So again, we can show that we get significant data efficiency and much better results. And we do this at much lower kind of complexity. That is, the number of parameters is pretty low, and our iterations per second is also pretty low. Okay, and we could try to understand what this is doing. And again, we have this hierarchical attention. And so what we intuitively want to do is, for example, attend over the different views. So sometimes the object detections might be important. Sometimes the image level information might be important. Sometimes the textual information that we retrieved might be important. And so we want the model to dynamically switch between these. And we show, for example, when we add noise to different views, it does indeed reduce the view attentions. And similarly, if we, for example, decode the word dog in our image caption, if we remove the pieces of information from the image, for example, mask out the dog, that view, the image view, is going to be much less emphasized in the model. Okay. So that's the image captioning part. Again, the key idea is we want the robot to describe what is in the image. Now we want to have the robot take in, feedback from users, for example, some form of labels or even just unlabeled data that the human says is important, and have the robot automatically learn about new categories. We can frame this in the computer vision community as category discovery. We also had named this cross-task transfer learning in the past. This is kind of older work that we've done at iClear 2018, 2019. And here the problem is you have some labeled data sets. You can have, for example, of course, ImageNet or CIFAR and so on. And you can have some portion of that labeled in terms of the categories, but now we have unlabeled data. And eventually we'll talk about the semi-supervised case or generalized category discovery, where you have both labeled and unlabeled, or the unlabeled can contain both known and unknown. But here, for example, we just said the unlabeled can contain unknown categories, and the key idea is we want to cluster or discover those categories. So we developed a bunch of different approaches to this, including using similarity-based learning. However, since then, a lot of great groups have followed up on this to do what's called generalized category discovery, where again, the unlabeled data can contain both known and unknown categories. And some can be labeled and some can be unlabeled. So this is kind of a much more generalized form that's much more realistic when you're interacting with a human. The human can label some portions. They can, for example, point to scenes that the robot can generate or can gather unlabeled data from, and so on. And so now we can actually leverage, again, the point of this workshop, which is cross-modal information. We can, again, leverage CLIP to essentially retrieve information from these unlabeled images and try to discover categories much better. And the reason we can do this is now we have images encoded in a joint feature space combined with textual information that we can retrieve, again, encoded in a similar feature space, because that's what CLIP allows us to do, align these feature spaces. And we can do not just clustering, but we can actually jointly cluster different elements together, such that we cluster the labeled things that we know about, and at the same time, we can generate clusterings of the unlabeled, unknown things as well. And so again, we can do something very similar as before. We can actually just use CLIP in a straightforward way. So GCD is, again, this generalized clustering or category discovery paper that was from CVPR 2022. And actually, if we just use CLIP by itself, because CLIP is really good at zero shot, we already get some gains. But we can also do, again, the same idea as what we described previously for image captioning. We can take the image, we can retrieve contextual text information, and we can now do a joint clustering over this. And we again show that we can get much better clustering results. So here we separate results based on the old known categories that were labeled. Of course, the unlabeled data had some examples there too that were unlabeled. And then also the new categories, which are completely new. Nobody has ever given a labeled example of that category, but existed in the unlabeled data. And we were able to essentially cluster those instances much better using this retrieved contextual text knowledge. Um, One thing to note is that thus far we don't really name these categories. I think that's an interesting area of research where we now discovered new things in the environment. Now we want to name those things and actually communicate that to the human. Okay. Um, the other thing is, okay, now that we've discovered new categories, we want to continuously learn about these. And this is a tricky thing to do because ultimately we know that neural networks can forget. And so this is sort of the field of continual or lifelong learning. Again, typically, if we train a neural network offline with lots of known categories, that's fine. But if we want a robot to continuously learn after interactions with a human, then we want it to continuously learn. And so we know that there's this problem called catastrophic forgetting, where you forget old things that you've learned about as you're learning new things that, for example, the human is telling you about. And one of the key kind of things that we want to do is essentially, again, learn incrementally from a stream of tasks that or categories that we get. We do not necessarily want to store past data. So this is replay is a popular way to do it. That is, you just store past examples that you've learned about as you're learning about the new things, and you just sprinkle in that old data into the learning, into the mini batches while you're learning about new things. And so there's a lot of reasons why you might want to not do this. For example, privacy. Sometimes if we're interacting with a human in the home, we may not want to essentially learn, or sorry, store past data that may contain private information. Um, and so again, we want to avoid this popular method where it does essentially internal replay. Okay. And so one of the key interesting ways that we've done this, and this is something that was originally developed by other people at UIUC and other places in 2020, is this deep dreaming idea. That is, we want to essentially take a discriminative model and somehow generate data from that. And you can do this by essentially backpropagating to an image. That is, you start from a random image, you feed it through the model, and you essentially try to maximize some score of a class, and you essentially then optimize the image itself to generate examples of that class. And so that's how you can essentially generate new images of old things that you've learned about. However, there's a problem, which is, and this was mentioned in that original paper as well, that this deep dreaming fails for incremental continual learning. And so I won't go through the method because really I'm just trying to give you the gist of the ideas that we've developed, and you can read the papers for more details. But the idea is we've improved upon this such that it actually works for continual learning. And really what we've improved upon is the fact that when you're generating synthetic data through a discriminative model and combining it with new data that you're learning about new categories for, really the model tends to just discriminate between synthetic versus real. And so we've developed methods that really aligns these two such that you no longer have this bias. And we can show that our method continuously learns new categories cumulatively much better than the prior methods. Of course, it's not perfect, and it's a really hard problem, especially, I mean, the replay of past data is really effective. Of course, to the extreme, it's just offline learning. And so, we're really trying to continue to push performance on this through various methods, including better generation methods through large-scale models. We've also looked at semi-supervised continual learning, again, under the idea that you as an agent in a home interacting with humans will inevitably gather lots of unlabeled data. And so again, instead of doing replay from past tasks or categories that you've known about, why not just use unlabeled data and then do pseudo labeling, that is make predictions on it and use that as replay. Again, I'm not going to go through the architecture, but it uses combinations of unlabeled and labeled data through a various sets of losses, distillation and consistency losses, to do semi-supervised continual learning. And we can do much better, again, than prior methods, including prior semi-supervised methods that gathered unlabeled data from the web. One of the things that we show is that gathering data in a correlated way, because in the home environments, for example, your unlabeled data will be correlated with the new things that you're learning about. The labeled data, prior methods did not work, whereas our method does much better. Okay. And of course, a lot of that work we did in standard computer vision settings where you have images and image classification. One of the things that we've done recently in a workshop paper is essentially expanding this. Sorry, the citation is incorrect here. This is in CL Vision 2022, is looking at what happens if an agent is wandering around, getting some sparse set of labels, but also gathering unlabeled data and learning about new environments. So we add this learning over mixed unlabeled and labeled data, but we also add new instances and categories appearing across an environment through natural data distributions as an agent would encounter them, which I think is really important to study as well. Okay, so with that, I'm going to wrap up and take some questions. In summary, I think there's a rich potential for human-robot interaction, especially when we add language. So language has the ability to obviously provide means of communication from the robot to the human and from the human to the robot, but also it has this ability that people are looking at, including our group, for zero-shot learning or open world learning. That is, it's really giving us this boost of generalization that just vision only is not able to handle. And I really do like this loop of thinking about how the robot can communicate to the human what it's seeing through things like captioning. It can ingest human instructions or feedback, again, through natural language. And then it can also use natural language and these clip-based and other multimodal models to retrieve contextual information from the World Wide Web or any textual information to provide context and grounding. And this really improves zero-shot discovery, especially through these cross-modal models. And of course, we inevitably also want to do continual learning. Of course, I should say, adding all these things together, again, these are ingredients that I believe are important for cross-modal human robot interaction. Combining all of these in a large, grand, unified manner is, of course, very difficult and not something that we've done thus far, and really we're moving towards as we continue to do work in these spaces. So with that, I'd like to thank the funders, collaborators at Meta and other organizations like Samsung, and all of my PhD students who, of course, do all the work. And with that, I will take questions. Thank you very much.